The next speaker is Amin Babadi. Yes. We will talk about self-imitation learning and locomotion movement through termination curriculum.
Okay, hello everyone. My name is Amin. I'm a PhD candidate of computer science at Auburn University and a visiting researcher at the University of British Columbia. So this is the work that I've done with the help of my colleague Kourosh Naderi and my supervisor Perttu. There are two different approaches for synthesizing animation. So the more traditional approach is called keyframe animation, where the animators define a number of keyframes, and each keyframe specifies all the joint angles for the character. And then by interpolating through these keyframes, we can produce animations. And this is the most popular technique in producing animation for games, but it has some limitations. For example, because the keyframe animations are not responsive to the environment, we can see some certain behaviors like this in different games, because the characters in keyframe animation cannot actually interact with the objects around them. On the other hand, we have physics-based animations. So in this category, we have characters, and we can control these characters through applying torques to different joints. And the animations are then completed by physically simulating the environment. So that's why these animations will look a lot more natural, and they are very useful in games such as FIFA, where the physical interactions are an important part of the gameplay mechanic. So there are a ton of work in the area of physics-based animations. We can divide them into two categories. The first category is planning and search, where we just use a search algorithm for finding the best sequence of actions, and in the category of reinforcement learning, we want to learn a policy through interaction with the environment. So here I'll only point out to the most relevant work to this paper. In the category of planning and search, we have FTI MCTS. This method was developed in our lab in Finland, and this is just an online optimization method inspired by Monte Carlo research that can be applied to any characters, and you can just apply some perturbations to the agent that can just produce robust walking animations. And in reinforcement learning, we have this method called MIG. This method uses some high-quality motion capture animation, and then uses reinforcement learning to find a policy that can imitate that reference animation. And the main motivation behind our work was to somehow combine these two approaches together to use the advantages of both, because in FTI and CTS, we don't need any motion capture data, and it can just work with any arbitrary character, but it's kind of CPU intensive, so you cannot actually use it in real time. But Deep Mimic, once the training has been finished, you can easily use the policy in real time, but you have to have this high quality reference animations. So in our category, in our method, we take the character and we apply online optimization. In this case, we applied FTI MCTS to produce this walking animation. After some time, this animation becomes robust and smooth enough. After that, we apply an automatic cycle detection procedure to extract this short walking cycle out of this synthesized animation. And after that, we apply reinforcement learning, and in this case, Deep Mimic, to find a policy that can actually imitate this reference motion. So we call this process self-imitation learning, because in this case, we are actually imitating, the system is imitating the behavior that it produces itself. So now I just explain each one of these steps in the next slide. So in the online optimization stage, as I said, we use FTI MCTS, which is just a sampling-based algorithm for continuous control. and it does not use any motion capture of the recorded animations. So it can just be applied to any kind of characters that you want. And it can produce stable walking gaits after a few minutes. And this is the example that I showed earlier. So this method is a two-step iterative process. So in the first step, it does a tree search, similar to Monte Carlo tree search, for finding the best action at each step. And then it tries to memorize the best count action using supervised learning. After a few minutes, this supervised learning component converges to the good solution. So the movement becomes smooth after just like 2 or 3 minutes usually. So once this we have this smooth gait, we want to extract a walking cycle out of this. So for example, suppose that we have run the algorithm until here for 2 minutes. After that, we say that, okay, right now the movement is good enough, now we want to extract a cycle out of it. So we mark this frame as the start of the cycle, and we go on until we find the end of the cycle. For doing that, we store the position and linear velocity of each end effector, and just compare this information with the initial frame of the cycle. And we go on until we find the final cycle. So it just rejects these states until it finds a state that is similar enough to the initial frame. So far we have found a good cycle. Now we can apply reinforcement learning for actually imitating that cycle. For this we actually use MIG, and we use DPU as our main training algorithm. And we use the same reward function, almost the same reward function, reference state initialization and early termination as introduced in DPMIG. But when we applied this, we found out that this actually is super slow to train. So we wanted to improve the sample complexity. So we came up with a curriculum learning approach that we call Termination curriculum, which I explain next. But for explaining that, I need to at first tell you how reference state initialization works in DPMIG. So suppose you have this 2D state space, and the dark sine curve is the reference motion that I want the policy to follow. So if we just start all the episodes from the starting point of the curve, this is how the random walk will look like, because the policy is just bad and it just goes after reference trajectory all the time. So reference state initialization proposed by DPMIG means that we can just uniformly pick points on this reference trajectory when we want to restart an episode. And this has shown to be very effective for increasing the learning speed. So we took this idea a bit further, but by defining the threshold on the amount of deviation that we are allowed to do from this reference trajectory. So these red dashed curves actually show this type threshold that we are using. So this type threshold in the beginning of training means that we will have a lot of short trajectories, because once I come out of this threshold, I just terminate it, so then I start again. And once as the training goes on, I will loosen this threshold. But since the policy has been being trained, so it has learned to somehow stick to the reference trajectory to some extent. So hopefully this will not be as bad as the situation here. So by doing this simple mechanism, we can keep the training algorithm to avoid the simulation budget in ruthless regions of the state space, because these regions are not going to be visited by the optimal policy anymore. For the experiments, we used Open Dynamics engine as physics engine and Unity 3D for rendering, and we did the simulations in 64 threads. The state features contain position and orientation of pelvis, angular velocity of each bone, and the joint angles. And for actions, we use reference angles and P-controller, which is a very common way of doing so in physics-based animation. And the simulation and control frequency are both set to 30 Hz. And we use TensorFlow and OpenAI baselines for reinforcement learning. And the source code is available at MIG. So, as I said, we can just apply this method to any arbitrary character that we want. So we just pick these three characters, And you can see the simulated rig of each one of the characters right next to it. And we use 3D capsules for simulating the bone. And the joints are either 3 degrees of freedom ball and socket or 1 degree of freedom hinge joints. So this is the result in terms of the reward. So the green one is the one using termination curriculum. So in this version, at the beginning we set the threshold, the reward threshold to 0.75 and then reduce it to 0.5 throughout the training. And the red one is the baseline without the termination curriculum. And as you can see, termination curriculum is actually improving the performance in terms of the speed and the reward significantly. And to see how the training output looks like, this is the initial policy that we have. And this is after 50 bucks. This is after 1,000 bucks. And this is the final policy. And all of the pipeline, including the FDI, MCTS, and cycle detection and reinforcement learning was done over 3 hours, which is pretty fast. And you can see that the policy is doing a good job imitating the reference motion. And here is how the outputs look like for other characters. The main problem that we see here is the wolf character. And the reason is that this walking gait is not optimal for quadrupeds, but we couldn't fix it because FDI and CTS simply cannot produce galloping movements, so that's why we couldn't just fix that issue. But otherwise, I would say the other two characters are working pretty well. And to summarize, we propose an approach for constructing a controller for synthesizing the stable locomotion movement. So this approach does not use any motion capture or pre-recorded animation, so it can be easily applied to a wide range of characters with different anatomies. And it can find robust control in only a few hours, and normal PC. Actually, all of the results that I've shown were produced in less than 4 hours. And which is pretty faster than Deep Mimic, because Deep Mimic I guess did it in a few days for each one of the characters. And for future work, we still think we should decrease the sample complexity further, because if you want to use this pipeline in the video gaming industry, there are going to be a lot of changes to the animations, and it doesn't feel right that you need to wait for like 4 hours every time you get a new animation. So I guess we still need to make this faster. And it would be nice to extend this to more complex movements, such as galloping movement that I mentioned. And for doing that, one just has to replace the PI MCTS with another optimization approach, and then the rest of the pipelines should just work on. Thank you very much. Any questions?
Thank you. Any questions? Okay.
So, about this, so initial motion generated by your optimization method is faithfully plausible motion.
Yes.
Right. Is it possible, have you thought of doing supervised learning with this motion instead of like doing reinforcement learning on the kinematic motion that was produced by this first method?
Yes. That has actually been tested by my colleague, and he wrote this FDI MCTS paper, and no, it doesn't work in the 3D case because it's like super noisy problem. So supervised learning in this case doesn't work. So you have to deal with vertical reinforcement, and if you want to make a robust policy.
Other question? Thanks. For this 100 epoch training result, not this one, the previous one, I think there was one where the character stopped hesitate a little bit. I wonder if this happy accident or somehow you're trained to do that.
So what was the question?
So it walks, then stopped for a while, then. So is that like sort of a side effect of the training, or actually it's aimed for?
Yeah, it's just a side effect. I mean, what we're aiming for is this motion, so it has to have this constant velocity of 1 meter per second, I guess. So at some point it just cannot just realize at this speed. But after doing the training, it will happen actually.
last question?
Thank you for your talk first. I just have one question about the cycle extraction. So you said that you made the local optimization and wait for the motion to be good enough. And so I wanted to know if you use the objective criteria to define this good enough motion on which you extract the cycle and they use for the reinforcement.
So the question is what criteria we use to
define that it's a good enough locomotion.
Well, we tested this on like a number of characters, and it actually happened after only 1 minute. So we just let it run for like 3 minutes, and then just hit the cycle.
Thank you.
Okay, so let's thank the speaker again.